The Graham-Schmidt process is an application of orthogonal projections which produces an orthogonal basis for any non-zero subspace of Rn. After studying the Graham-Schmidt process, we'll apply it for QR factorization of matrices. See this example. W is a span of x1 and x2. x1, x2 are given in this way. They are apparently linearly independent. We'll try to find an orthogonal basis for W. The main idea of the Graham-Schmidt process is the orthogonal projection. For given two vectors, and x2 will be projected onto the space of x1, and this is the normal component. So x1 dot v2 must be 0. Of course, v2 is non-zero because x1, x2 are linearly independent. Okay, we rewrite here. v1 is x1, and v2 is x2 minus alpha x1. Then we know v1 and v2 are orthogonal, and they are a linear combination of x1 and x2, so that the spanned subspace of x1 and x2 and the span of v1, v2 must be the same. That means that this is originally a basis for W, but now this is a new basis and orthogonal. Okay. Now let's try to find an orthogonal basis for W. Okay. x2 must be projected to the space of x1. So x2 is the same as x2 hat, which is alpha x1 plus, now we are using v2, the notation. And alpha must be here, x2 is projected to x1, so that that's x1 dot x1. Okay, x2 dot x1, that is a 3. Okay, 3 plus 12, so that is 15. Now x1 dot x1 is 9 plus 36, that is 45, so we have 1/3. Okay, so v2 must be x2 minus 1/3 of x1. Okay, x2 is 1, 2, 2, and 1/3 of x1. That's 3, 6, 0. Okay, so that makes a 1, 2 with 1/3. So here remainder part is only the last one. Okay, that's v2. So if we collect here the x1, which is v1, that one, and that v2, then that is an orthogonal basis for W. Pictorially, we can explain that process in this way. x1 is this one, and x2 is this vector. And spanned by these two vectors will make a plane in R3. Now, rather than using x2, we project it here in x1, the subspace of x1, and then try to get normal component. So rather than x1, x2, we are using now that we rename v1 and normal component v2. These two orthogonal vectors will span the same space. right? Find an orthonormal basis for the subspace whose basis is given here. Orthonormal means orthogonal and normalized. So, okay, that is x1, that is x2. So x2 must be projected to x1, and then now normal component. And alpha, for this equation, alpha must be x2 is projected to x1, so that we have that one. x2 to x1, projection is there is 24, 0, and plus 6, divided by x1 dot x1, there is now 3, and okay, 9 plus 1 is 10, so that is 3. Okay, so here v2 must be x2 minus 3x1. Okay, x2 minus 3 times that one. Okay, for first one, that will be minus 1. Okay, the same as 5. And 3 times of that one, minus 3. So that plus 3, and that must be minus 3. Okay. Now, we already know that is x1 and v1. Now, we have to normalize them. So from here, u1 is v1 over its length, v1. Then, okay, yeah, that is 9 plus 1, 10. So length is 1 over, okay, length is square root of 10. And yeah, v1 is 3, 0, minus 1. And u2, we can get it from v2, normalize it. Now the length of this vector is 1 plus 25 plus 9, so it's 35. So 1 over square root of 35, and the vector minus 1, 5, and minus 3. So these two will be on orthonormal basis. Now here, we'll generalize what we did, and that is called the Gram-Schmidt process. Given a basis, that means that these are non-zero linear independent vectors, and for some subspace of Rn, we define v1 is x1. Now v2 is the normal component of x2 after projected to x1, which is same as now v1. So after projection, we move this projection to the other side, and that is the normal component. Exactly the same way, x3 will be projected to v1 and v2. They are already orthogonal. So we can make such projection, and that projection is now moved to the other side to get the normal component. So here v1, v2, or v3 will be orthogonal. And we continue, and because they are linearly independent, always these vectors are non-zero. And we go to for the last one. So that is now the vectors, orthogonal vectors. So that v1 to bphi, the set is on orthogonal basis for w. In addition, for any intermediate level k, the span of x1 to xk and span of v1 to vk must be the same, because vk's are vi's are gotten as linear combinations of xi's, so that these two spaces must be the same. Okay? For any k between 1 and p. Earlier we already know that span of x1, x2 is same as span of v1, v2. Again, span of the three vectors must be same as span of the three vectors, and so on. Okay? This is a Gram-Schmidt process which produces an orthogonal basis for W. Once the vectors, V vectors, are normalized, then the normalized vectors will form an orthonormal basis for W. Right? It's quite clear because this set is orthogonal and each one has length 1, so that the set must be on orthonormal basis for W. So this one is known as normalized Gram-Schmidt process. In reality, here the algorithm is implemented along with this normalization, so that the output is most cases orthonormal basis rather than orthogonal basis. Okay. Find on orthonormal basis for W, that is a span of x1, x2, x3. So we have to apply the Gram-Schmidt process to get orthogonal basis, and we can do it simultaneously normalization. However, in the case, the output will be along with the non-integer values, so it is a little bit complicated. So we'll try to get orthogonal basis and later on normalize. But in reality, normalization is involved inside, so that we can do it simultaneously. Okay, anyway. Here, that is now a V1. We got V1 already. Okay. Now, V2 is the same as x2 minus its projection to x1. In fact, V1. So that there's x2 and x1 divided by, okay, we may try to use V notation, and V1 dot V1, right? And that is here x1. And again, we'll use a V notation, V1. Okay, so first we'll try to get that portion. x2 is projected to over there, and then dot product minus 2, okay, minus 1, so that dot product is minus 3 divided by v1 dot v1, which is 3. Okay, there's a minus 1, so that there is simply x2 plus v1. That is, okay, we are adding 2, then minus 1, 2, 0, 1. Right? Okay. Now, so we got V2 now, and here, and V3 must be written in this way. That is now x3 minus alpha 1. Let's try to use notation alpha 1 V1 minus alpha 2 V2, where alpha 1 is x3 projection onto the space of V1, so that there's x3 dot V1 over V1 dot V1, right? Okay. Here x3 V1, which is x1, dot product will be 0, 0, 1 plus 1, so that there is 2. And V1 dot V1, we already know that is 3, so that now that is Okay, that's 2 over 3. Okay, now we'll go alpha 2. That is x3 is projected onto v2, not x2. You have to project the vector to orthogonal the bases. So you cannot use x2 here. v2 and v2 dot v2. Now x3 v2 dot product is 0, 2, again 0, and 1. So it is a 3. The bottom must be here v2 dot v2, 1 for 1. So it is a 6. That is half. Okay. So here we have now v3 is the same as x3 minus alpha 1, 2 over 3 v1 minus half of v2. Okay. So x3 is, let's see over there, that is 0. Start with 0. Okay. Okay. Expand it. That is 0, 1, minus 1 and 1, minus 2 over 3. v1 is now 1, 0, minus 1, 1, and minus half, and v2 is minus 1, 2, 0, 1. Okay. That is 4 over 6, and that is 3 over 6. So we may think that is okay. So 4 and minus 1, but that must be 3 is minus 3. So it looks like okay. 1 over 6 must be okay. So that must be minus yeah, that's negation and positive, so that okay, so it is a minus 1 over 6, I believe. Okay, and second one, okay, that must be 0, and third one minus 1/3, right? Okay, you can check it. Final one from here, okay, 6, and that is now minus 4, and again that is minus 3, so that again minus 1 over 6, I believe. Okay, so we have this one, and now that is v3, so it's not easy to deal with. Just you may try to get some scaling, then it's a minus 1, 0, and okay, minus 2 and minus 1, like that. Just a moment. 6 and minus 4, minus 3. Okay, so it's a minus 1 over 6. Okay, so we have that, and now if we want to get orthonormal, then for these 3, you can scale to become 1. So length is square root of 3, divided by square root of 3, which is u1, and divided by now square root of 6, and again divided by square root of 6 will give you 3 orthonormal vectors, which will form on orthonormal basis for W. Okay. QR factorization of matrices. Now we'll deal with A on m by m matrix, general size of matrix, with linearly independent columns. So practically m must be larger than or equal to n. Once m is smaller than n, you cannot get linearly independent columns, so that we implicitly assume that m is larger than or equal to n. Now, here the condition is it has linearly independent columns, then A can be factored as QR. Q is an n by n matrix whose columns are orthonormal, which means that Q transpose Q is identity. If M is larger than N, then it's not a square metric, so that it's not a orthogonal metric, but it has this property. And R is an n by n square metric, that is upper triangular, and the diagonals will be positive. So it is invertible metric. And this can be proved quite easily. First we get, because it has linear independent columns, we can get orthonormal basis for the column space of A. W is column space A, and this original columns will be a basis. Now from that, we can get orthonormal basis by using Schmidt process, and we'll collect them as Q. And now here, each columns of A will be projected along with that basis. Then we can make such expression, and from this expression, we'll try to collect Q and R. So that's it. That's the basic idea. And we can get QR. Here we have the algorithm for QR factorization. A has n columns, and the columns are linearly independent. Then we first apply the Schmidt process to obtain orthonormal basis U1 to Un. Then each column can be expressed as a linear combination of U1 to Un because they are orthonormal, and this expression is unique, in fact. And we can get such coefficients. X1 is, along with this coefficient, now U1 direction, and X2 is linear combination of U1 and U2 with that coefficient. Now here we collect the vectors in the orthonormal basis, and these coefficients are also collected. Then you can easily see that these equations are satisfied. That is exactly QR factorization. Here R has this one. Now this is U1 with X1, X2, and Xn dot product, and from U2, and again X2 to Xn, and so on in this range. In this construction, maybe some of this diagonal dot product may be negative. It can be negative. Then we can fix it. Earlier, okay, when we are working on such expression, once the sum of coefficients are negative, then we multiply -1 here and -1 here. That means that in QR factorization, we multiply on column of Q and -1, and now for here the quantity we multiply -1, then here it'll be okay. Both way, -1 is multiplied so that eventually it'll be cancelled, and then we can make the diagonal entries positive. Okay. Let's try to find the QR factorization for the metric. And here, this is X1, that is X2, And by using Schmidt process, we have to make orthonormal bases for that one. Okay, now x2 must be first projected to the space of x1, so which is alpha x1 plus v2. Okay, now alpha is x2 and v1. Of course, there is x1 yet. Okay, x1 divided by x1 dot x1. x2, x1 dot product is -4 plus 6. So then that is 2. That is 2. -4 plus 6. And x1 dot x1, that is 25. So here v2 is the same as x2, which is -1 to 2 minus 2 over 25, and x1, that is 4 and 3. You can see this one as, okay, 8 over 100, right? 8 over 100. So that here -1 minus that 8 times 4 is 32. So that minus 1.32. Right? Okay. Now for that one, and there's 8 times 3 is 24, and 2 minus that 24, there's 1.724. So that is a 76. Right? Okay. Okay. We got V2. So U1 is same as now x1 over norm of x1. Okay, from here, now length is 5, so divide by 5. Then there's 0.8 and 0.6. Now U2, that is V2 over V2 norm. Okay. For this one, let's see in this way. Looks like that is 3 times of 0.44, and that is 4 times of that. So that is -3 and 4. Okay. After scaling, again, now we may ignore this portion, and the length is 5 divided by 5. So that we have here -0.6 and 0.8. Okay, collection of these two makes that. Now, here you can find these dot products, or you may try to multiply here the Q transpose to A, and you can get R. Either way, you can get R. Your R is this one. Okay, you can finish yourself. Okay, now we reach at the true or false problem. Okay, part A, if V1, V2, V3 is an orthogonal basis for W, then multiplying V3 by a scalar C gives a new orthogonal basis. Is it true? Okay. Now, even though C is multiplied, the orthogonality is not changing. So we may say that it's a new orthogonal basis. But the problem is, it is saying a scalar. But once the scalar is 0, then the vector must be 0. So it cannot be a basis. Right? So that once the C is 0, it has a problem. So the given statement is wrong. The Gram-Schmidt process produces from a linear independent set an orthogonal set with the property that for each k, the vectors v1 to vk span the same space as that spanned by x1 to xk. Yeah, it's true. We considered this one, so that it must be true. Okay. A is QR, where Q has orthonormal columns. Then, now R can be gotten Q transpose A. Is it true? Yeah, why not? And it has orthonormal columns. Then, if and only if we know that here Q transpose Q is identity. So both sides, you multiply Q transpose, then Q transpose A is the same as R, right? Okay, so that's true. If X is not in subspace W, then X hat, that projection of X onto W is not 0. Is it true? Okay. Now here, and X is not in subspace W, then projection is not 0. It can be not 0. However, once X is in W prop, for example, so in 3D, R3, here we have a plane and subspace W. Now this is origin, and now normal, from normal direction, there is a vector. Okay, we use the same notation X, that's projected, then it'll become 0. Okay, so even though it's outside the subspace, the projection can be 0, which means that this statement is wrong. In a QR factorization, say A is QR when A has linear independent columns. We start with A having linear independent columns. Okay, A is QR. The columns of Q form on orthonormal basis for the column space of A. Is it true? Yeah, it's true. And in fact, the columns of A, they are linear independent, so that each, okay, let's try to write down A is here now x1 to xn, the columns of A. In the beginning, we assumed that they are linear independent. That means x1 to xn, these columns will form the on basis of the column space of A, right? From that on, and once we get QR factorization, Q will be is on orthonormal basis of column space A, so that exactly it is saying that, so it must be true, right? Okay. That's the end of the section. Thank you.